So now I want to talk about a kind of specialized but very common type of proof called proof by induction or mathematical induction. So if you're familiar with inductive reasoning versus deductive reasoning, again, something you'd cover in more like a critical thinking class. Deductive reasoning is what we typically are doing in math, where we kind of start with something general and then we work our way towards the specifics. So we start with a theorem and then we make our way towards examples, right? Inductive reasoning does the opposite, where it starts with something specific and it works towards something general, which is more something we do in statistics, for example, where we look at data and we make generalizations about that data. So that's inductive reasoning. So the same kind of principle applies here. We want to start with something small, specific, and use that to make a general statement. So the main process of induction is that given a statement on the natural numbers, so something that's like true on the natural numbers, okay, it's not going to work on the integers because of the nature of these proofs. It's really only going to work on the natural numbers. Prove the statement is true for the base case. Okay, so we call the base case the smallest such n in n. Okay, so if it's true for all numbers n greater than or equal to 1, then you prove it for n equals 1. If it's true for all natural numbers n is greater than or equal to 10, then you prove it for n equals 10. Whatever the smallest one you can get away with is, basically. So that's your step 1, is you prove what we call the base case. 2, assume it is true for n. Okay, so this is a little bit weird because typically it's a statement about n. So we assume it is true for some general n. And we use that to show, well, I guess this is really the same step. Then show that this implies that it is true for n plus 1. Okay. So this one can be summarized as the base case. This one can be summarized as n implies n plus 1. Okay. So think about why this would matter. So let's just consider that it's true for, we get some statement and we want to show that it's true for n is greater than or equal to 1. Okay. Well, if we show that it's true for 1, and then we show that if it's true for n, that implies n plus 1 is true, then that means that 1 would imply that n equals 2 is true, because n implies that n plus 1 is true. And then 2 implies that n equals 3 is true. And then 3 implies that n equals 4 is true. And that's going to keep going on forever, right? So this is sufficient to prove whatever statement it is we're looking to prove. Okay. So let's look at an example of, where this would come into play and how this would actually look in action. So let's say that we want to show that for all n in n, 3 divides 4 to the n minus 1. Okay. So what we'd do here is first we'd prove the base case. The base case here would just be n equals 1 because we want to show that it's true for all n in the natural numbers. So we need to show it's true for the smallest one. Okay. So if n equals 1, this implies that 4n minus 1 is equal to 4 minus 1, which is 3. And clearly 3 divides 3. Okay, so we're done. Okay, not really much to do here, and that's typically how it'll go for the base case. The base case is typically the pretty easy part of the proof. Now what we do, so maybe we write now, assume that that 3 divides 4n minus 1. And then we want to show that 3 divides 4 to the n plus 1 minus 1. Okay. So we kind of have two things to work with here, right? We have that this is what we're building towards. But this is our assumption now. So this kind of gives us a lot to work with. It might be helpful to know. I don't even know if it will be because I don't have the proof laid out in front of me. But it might be helpful in these cases to, note that this is going to be true, right? That's 4 to the n times 4 minus 1. We might be able to do something with that. So just the kind of things we want to look out for, keep in the back of our mind here. So if 3 divides 4 to the n minus 1, we saw this kind of idea earlier. This means that 4 to the n minus 1 is equal to 3 times k, right? For some k, technically in the integers, you keep it in the natural numbers if you want. It doesn't really matter too much. But we're mostly working in the natural numbers right now. So we know that this is true. So this gives us an equation to work with here. And we know that this is kind of what we're aiming towards. So maybe it would be helpful to multiply by 4 and then see where that leaves us, because we need to get that 4 in there, right? So we'd say, okay, well, this implies that 4 to the n times 4 minus 4 equals 3 times 4 times k. Okay, so just inserting that 4 everywhere, basically. I'm not going to combine these yet because we probably are going to need this 3 times something form. Doesn't really matter. We could always factor it out later, but that's the reason. Now, this and this are not the same thing, right? We still have this minus 4. So now maybe we just add 3 to both sides and then see where that leaves us. So now we have 4 to the n times 4 minus 1 is equal to 3 times 4 times k plus 3. So now this side is just 4 to the n plus 1 minus 1. And now this side, we can factor 3 out of the whole thing, right? And then we have this. Now, 4k plus 1 is going to be an integer. So by the definition of divisibility, this implies that 3 divides this whole thing right here, right? Because this is the definition of divisibility, that it's equal to 3 times some integer. So then we're done here. So we showed that this is true for n equals 1. We showed that if it's true for n, then it must be true for n plus 1. So this means that, okay, well, it's true for 1, which means it's true for n equals 2. Let me say this. N equals 1 is true, so that implies n equals 2 is true. So that implies n equals 3 is true. So that implies n equals 4 is true, etc. Right? All the way to infinity. Okay? So this is sufficient to prove that 3 divides 4 to the n minus 1. So this can be, kind of, I think it's a very logical framework. I remember when I was first learning this, I kind of glossed over a lot of the details. I didn't really realize why we needed the base case. But I think if you, now, I think hopefully just thinking about it like this helps you understand it. It might seem simple, but it's easy to gloss over, like what exactly is happening here. So because of this, it's important to start at the very beginning. Like, because I didn't really understand the base case, sometimes I would just take like n equals 3 and prove that if it was easier. But then you're missing the first couple, right? So if it gives you a statement that's true for n is greater than or equal to 3 or something, then n equals 3 would be your base case. So in that case, you would do it. But otherwise, we need to start at the very first one, which in a lot of cases is going to be n equals 1. But this is, this is pretty much anytime you see something happening on the natural numbers, induction is a good, it's a good guess for the kind of proof that you're going to need to do. Not 100% of the cases, but a lot of the times it is. And it's just really nice compared to other proofs, because the other proofs, you're kind of just have to like make stuff up on the fly. Like, you have stuff to work with in the hypothesis, but you might have to pull from different areas, and, you have to kind of be creative with it. Induction is kind of, what's the word? It's an attractive proof type, because, it's very logical. There's steps to follow, and with the assumption usually comes something, really nice to work with. And then usually you're just doing a little bit of algebra and you just go from there. So it flows really nicely. It's a good one to try to use if, it's possible. So let's do another example here. Another common type of these proofs is to show that a bunch of natural numbers sum to something. So, for example, maybe we want to prove that 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2. Okay, I think we looked at this one in the series section of Math Tools 2. I'm not 100% sure, but this is a very common finite series. So, maybe it's good to just give this a name just so we can talk about it. So S of n. So first we'll show the base case. Okay, S of 1, that's going to be equal to 1, which if you plug that into this formula here, that would be 1 times 1 plus 1 over 2, which is equal to 2 over 2, which is equal to 1. So we see that this one it's true. All right, we know that 1 is definitely equal to 1 plugged into this formula. Now we're going to assume that S sub n is equal to n times n plus 1 over 2. And now what do we need to show? Well, we need to show that S of n plus 1 is equal to this with n plus 1 plugged into it. So this is going to be n plus 1 times n plus 2 over 2. Now, it might be helpful to, multiply this out and see what it is. We'll see if we need to do that. For now, let's note that S of n plus 1, so let's say this is the proof here. S of n plus 1, this is equal to S of n plus n plus 1, as we saw in the series section. We know what this one is, S of n. This is equal to n times n plus 1 over 2. And now we need to add n plus 1 to it. So we're basically just hoping that this ends up being the same thing as this. So we could find a common denominator here, multiplied by 2 over 2. Okay. So this is going to be, just carry this part over here, plus 2 n plus 2 over 2. Okay, or let's just say 2n plus 1, because I kind of see where this is going now, right? Because now we can combine these into one fraction. So we have n plus 1 plus 2 n plus 1 over 2. Now the n plus 1 is a common factor, so we can pull that out. And we get n plus 1, n plus 2 over 2. Okay? Which is exactly what we wanted to show. So that means that the proof is complete. Maybe you'd put a square down here or whatever. And we have proven this formula. So this is the typical kind of thing you do with induction. Like you prove some formula. Like maybe you prove a formula for the nth sum. Maybe you prove a formula for the nth derivative or the nth integral. Maybe you prove that some number divides something with an n in it, right? These are the kind of typical proofs we would see with mathematical induction.